Yes.
So good afternoon, everyone. I'm Andrew, and today I'm going to present the Generative Multiview Human Action Recognition by Wang et al., published on ICCV 2019. So this is going to be the outline of my presentation. After the introduction, I'll talk about the related works, the proposed method, then I'll show the experiments, and finally the conclusion. So the action recognition is the identification of different action from video clips. So here we have two famous data sets, action recognition data sets. First one is UCF 101, the other one Connect 600. So we can think of action recognition as a natural extension of image classification tasks. So as this is a natural extension of this image class, the most intuitive way we have to solve this problem is to extend the networks we have for image tasks. So, so on this case, like we can use LSTMs to handle the problem for each of the frames, or we can even use like a 3D convolutional neural network. That's the extension of the 2D convolutional neural network that we have. These are just some examples of how to solve this problem. So both of these examples are based on single view. That means that they only use one modality of inputs here. On this case, they are using just RGB. So now we also have the multi-view scenario. So multi-view is when we have complementary information among different views. So for example, on a web page, we have the URL and the HTML file itself. So we can also think about a web image as the image itself and the surrounding text. Another example is when we have multiple viewpoints of the same scene. And a video clip is composed of the video frames and the image frames and the audio. And we also can have like a document with multiple languages, so we can see each of the language as a different view of the same document. So the multi-view action recognition can be divided into two categories. The first one, when we have multiple sensors from the same visual modality, that where we have surveillance cameras, for example. And the other category is when we have different types of sensors, like RGB, depth, skeleton, among other views. So in this work, the authors choose to use both RGB and depth as inputs to solve the action recognition problem. So RGB depth action recognition has become one of the most important research directions, especially after the popularity of depth 3D sensors and their corresponding applications. So the first example is on Microsoft Kinect that has an infrared camera and also an RGB camera. Another example is Intel RealSense that also have infrared cameras and RGB cameras as well. So now I'm going to talk about some related works. This first one, time-aware and view-aware video rendering for unsupervised representation learning. So the main idea of this work is to synthesize an unseen view from known views. So for that, they have activities captured from different viewpoints. And then they use video clips at arbitrary times to learn scene dynamics representation using their proposed representation learning network. And then from an arbitrary query viewpoint and time, they render a video using the proposed video rendering network. So then they can generate a clip from on this unseen view here. So the other related work is unsupervised learning of view-invariant action representation. This one is also focusing on generating unseen views from known views. So to learn the 3D optical flow of the video. So they proposed an unsupervised learning framework to learn the video representation. So they can predict the 3D motion in multiple target views from a source view. So for a sequence of inputs frames here, the encoder generated features that get passed both for the decoder, the cross-view decoder and the reconstruction decoder, and as well to the view classifier. So then the network is trained. So the encoder learned how to generate a view-invariant representation that capture the motion dynamics. So now this third work is dividing the aggregating network for multi-view action recognition, the DANet. This one is focus on solving action recognition problem. So from multi-view videos as input here, they train view-specific classifiers for each of the views, and then they use a weighted score fusion to output the final action class score. So the last of the related works is PM-GANS, discriminative representation learning for action recognition using partial modalities. This one also main goal is to recognize actions. So for that, they generated a full model representation using data only from partial modalities. So in this case, they use the infrared video clips here that are passed to the generative net that's going to produce fake features that's comparable to the visible features that they have here. So here they have the discriminator. And then the predictor uses the infrared features and the generated features to predict the action class. So as you can see, most of the multi-view existent approach rely on cross-view. They try to learn a view-invariant representation of the video, and some of them are based on generative learning, so they can learn unseen views from known views. So, but the main goal for almost all of them is to extract good features from each modality. So the challenge of the multi-view action recognition is that we have distinctive properties among different modalities. So there are some scenarios that we have incomplete or missing view sequences as well. And if we do view-specific predictions, it might be inconsistent sometimes. And also, if we're naively fusing multi-view features that could induce a negative effect, like if we do a simple concatenation or summation, it could harm the model performance. So to overcome this challenge, the authors proposed three major components. So the first one is the view-specific encoder to address the problem of to learn the different features from each of the views. The next one is a cross-view adversarial generator. So it can handle the missing incomplete view sequence scenario. And the last one is a view correlation discovery network that instead of just summing or making a sum or concatenating the results, they try to discover the cross-view correlation between the views to output the final label prediction. So the first one here, the view-specific encoder, seeks distinctive action representation in subspaces. So they have the input sequence on each of the views. So we have a view-specific encoder for each of them that then are going to extract features in the view-specific subspace. So it uses a triplet loss. So this loss makes the features that be closer on the space to the other features that belong to the same class. So here we have like a group of features belonging to the same class, and here is another class, and so on. So the cross-view adversarial generator, it increases the cross-view representation diversity, it enhances the model robustness, and it handles missing or incomplete view sequences. So the way it works is from a specific view subspace here, it generates fake samples on the other view. So from a sample on RGB subspace, the generator generates a sample on the depth subspaces and the other way around. So the discriminator and the generator D loss are the regular GAN losses that we already know, and but they also have to impose a similarity constraint for the generator, because especially on the first part of the training, the samples keep changing as the encoder is being trained. So for that, they created this generator similarity loss that enforces that the samples, the fake samples, become similar to the real samples. For the overall loss, they also have a lambda parameter here, so then they can weight it during training time. And the last component, the view correlation discovery network, it begins after the view-specific classifier that outputs the initial prediction for each of the views. So then a cross-view discovery matrix is created. So this is a pairwise label correlation matrix. And this matrix is passed to the view correlation discovery network that explore the latent high-level label correlation to output the final label prediction. So we can start here for the classifier losses. We have a loss for the classifier for the real samples, and we also have a different loss for the generated samples. So here the overall classifier loss is the summation between them two, weighted by a beta parameter. But on this case, beta is 0.5. So it's the average between the real and the generated loss of the classifiers. So they use a similar strategy here for the view correlation discovery network, where they have losses for real and cross real samples. That means that here is when we have a real sample come from the RGB subspace and real samples coming from the depth subspace, and they also have like this kind of loss when we have real samples come from one of the views and fake for the other one, and also fake from the RGB and real for the depth. Then they use a gamma parameter to weight it during training as well. So this is the complete framework here. So we have the input sequences here on each of the specific views. We have the view specific encoder that extracts the features into the subspace. So the generative loop is responsible to generate samples from one view subspace to the other one. Then these features go to the view specific classifier. So we have the initial predictions here that are combined on the cross view discovery matrix, and finally go to the view correlation discovery network. So here we have our final label prediction. So now I'm going to talk about the datasets that they are using. First one is Berkeley Multimodal Human Action Database, MH80. So this dataset is composed of RGB, depth, skeleton, acceleration, and audio views. It has 660 action sequences divided into 11 categories. So here we can see a schema of how they generated this data set. So we can see that they have multiple cameras here, also microphones, impulsive motion capture system, accelerometers, and also Kinects here on the corners. So they also use a UWA 3D multi-view activity dataset, UWA. So this dataset vary viewpoints, self-occlusion, and it has high similarity among activities. So as we can see here, like a phony answering is similar to the drinking activity. So this dataset is divided in 30 classes and has 10 subjects. So the last data set that they tested, so it was a depth included human action data set, DHA, that's composed of RGB images, human masks, and depth data. It has almost 500 video clips divided into 23 categories and 21 subjects. So we can see that the data sets are quite small, and they also have to use half of the available samples for training and another half for test. So the way they divided the training set they are using both RGB and depth information on the training set, and they divided the testing set into just single view, where either they use just RGB or just depth, and they are also testing into multi-view. So on the experiments, when where they only have single view, like they only have RGB, like this case here, the generative loop is responsible to create the features on the other view. So we got the features that is on the RGB subspace here and generated on the view subspace, on the depth subspace. So the same occurs when we have only depth. They generated the RGB features, and they are also experimenting it on multi-view as well, where they have both RGB and depth. So this is the performance analysis. We can see that that their model outperforms in almost every test scenario and in almost every data set. So we can see especially that on the RGB plus depth in scenarios of multi-view, it's achieved really good results, like much higher than the other methods, but they also it also gets like good results on single views as well. So the authors also realized some ablation studies. First, starting with the VCDN studies, they changed it, like they used different label fusion or correlation learning models, like feature or label concatenation and label average and weighted fusion. So at first they removed all the generated samples from their models, and then like on these first rows here, here we have the values for the view specific classifiers, both for RGB and depth, and then here on the next row they are concatenating the features after the encoding, and the next one they are concatenating the features straightforward. Here they are concatenating the labels. Then the next row, they are doing label average fusion. And the last one, they are doing weighted summation fusion of the labels. So we can see in all the scenarios on the three data sets that their VCDN achieve a much higher result, much better result than the other ones. So they also tested to replace their VCDN to regular neural networks having 1, 2, 3, and 4 layers. And in all scenarios, VCDN works much better than the regular neural networks. So they also performed some generator studies where they evaluated their model accuracy with and without the GAN part. So we can see that and they are testing it both for single views and for multi-views, and we can see that on all scenarios the accuracy with GAN is much better than without GANs. So that proves that the generative network of their model is not only good to generate it to handle the missing or incomplete view sequence scenarios, but also to increase the model performance. And they also have this t-distributed stochastic neighbor embedding visualization here, where we can see the generated samples represented by a plus sign that are really close to the real samples in both of the subspaces here, both for RGB and for depth. So now these are the main contributions in the conclusion. So the framework can handle complete view, partial view, and missing view scenarios. Generative adversarial training enhances the accuracy and robustness of the model. VCDN learns the interview and cross-view label correlations in the higher level label space and improves the model performance. And the generative multi-view action recognition is an effective, accurate, robust framework and compatible with a wide range of multi-view action recognition tasks. So that's it. Thank you all.